Hi everyone. So this is an extra video for those of you who kind of really care about maths and want to know the truth behind why sin x differentiates to cos x. Because the small angle approximation that you might have been taught, and that is the one you need to use for your exam, is a little bit of a fudge because you don't really know what the Maclaurin series is and you don't really know about complex numbers. And if you were also kind of shown the graph of why sine differentiates to cos, that's good like anecdotally, but it's not actually a proof. So we're going to do the official proof here, all right? And it all starts, just like everything, from first principles. So f dash of x is the limit. I'll use h this time. Normally I use delta x, but I know some of you use h. So f of x plus h minus f of x all over h. And our quick check of the differentiation table. So we really should know this off by heart now. So a to the x goes to a to the x ln a. Remember ln is just log base e, isn't it? E to the x, that lovely function that differentiates to itself. Ln x, 1 over x, sine x goes to cos x, and that's what we're going to prove. Cos x to minus sine x, why minus? Because it starts with a co. Sec, we know sec squared is 1 plus tan squared. We know there's a connection between sec x and tan x, and that's exactly what it differentiates to, sec x, tan x. This begins with a co, so cosec has to have a minus cosec x, cot x, tan x, sec squared x, again that link between tan and sec. Cosec, cot, sorry, begins with co, so that's minus, and cosec squared x, all right? So we're going to prove this one formally today, because once you prove that, then you can prove everything else, all right? So, f of x is sine x, yeah? So then f of x plus h, just filling in my ingredients, is sine, whatever's in the bracket replaces x, so x plus h, right? So this is going to go in here, and this is going to go in here. So I get f dash of x is the limit, very important we keep that limit in there. F of x plus h, so that's sine x plus h, subtract f of x, which is sine x, all over h, okay? Now, in your small angle approximation one, you would normally expand that out using the addition formula, but again, that's a bit of a fudge to do that. So we're going to do the proper way, which is using the factor formulas, which you may or may not have seen. They used to be in the old A level, okay? And it's to do with the sum of sines. So this is just a formula derived through the compound angle, so the addition formula. So you get sine p takes sine q. This is the same as 2 cos p plus q over 2 sine p minus q over 2. So that's an established formula that I'm using now. But what is p and what is q? Well, here p must be x plus h and q must be x because we've got sine something minus sine something. So this is the limit as h tends to 0 of just literally going to the formula 2 cos p, which is x plus h, plus q, which is x over 2, times by sine p, which is x plus h, subtract x over 2, all over h, remember, right? So, cleaning this up, limit as h tends to 0, cos x plus x is 2x divided by 2 is cos x plus h over 2. Can you see that? Sine x minus x is goes, and you're left with h over 2. H, and there's a 2 on the outside. Now, notice in here there's an h over 2, and in here there's an h over 2. So you'll see as part of the proof why I'm doing this. I'm going to write this h on the bottom as h over 2, and remove this 2 from the top. Because think about it, if you do something divided by a half, the 2 flips back up, doesn't it, to where it starts from. So I haven't changed anything. I've just done a bit of fancy rearranging. Now, strictly, when you take limits, you need to do the limit. If you're doing multiplication, it's actually true. What you're really doing is the limit of the first thing times the limit of the second thing, which is this. Okay? Now, this is the trick. This is the problem here, because if I take the limit as h tends to 0 on this left-hand bit, if h is 0, I'm just left with cos x, aren't I? But the problem is this right-hand side, because it looks like I'm dividing by 0 if I take the limit of h tends to 0 now. But the problem is, or the key thing that we're actually trying to prove here, is that sine h over 2 and 8 over h over 2 when h tends to 0 is actually 1. And, you know, it's hard to understand why that is. And because what we're really trying to do is to see whether sine h over 2 as h tends to 0, remember from the left or the right hand side, tends to 0, which one goes to 0 first? Or maybe they go to 0 at the same time, do you see? Towards 0 at the same time, and therefore you're dividing one thing by the same thing. So that's the difficulty, because if the bottom one, this one, went to 0 first, then we'd be dividing by 0. If the top one went to 0 first, you know, as you get closer and closer to 0, so h is like 0.001, 0.00001, 0.0000001, do you see? Maybe the top goes to 0, and therefore you've just got 0 over something, so that's just 0, do you see? This is the key bit that we need to address. So if we move on to the next slide, we're going to use, I did say this is proper maths, we're going to use the squeeze theorem. Okay? So how does the squeeze theorem work? Is if you imagine I've got a sector here, this is radius r, with angle h over 2. Why is it h over 2? In radians, remember, differentiation and calculus always needs to happen in radius. Because the h over 2 is the angle that we're concerned about, and you can see now why I've put h over 2 in that way. So what I'm going to do is I'm going to draw a triangle like this through the sector and a right angled triangle on the outside of the sector. Okay, so can you see that? I've got a triangle here of radius within the sector, so it's got side lengths r and r. And I've got a right angled triangle going up here. So what we're going to do is we're going to prove that the area of the sector is squeezed between the two triangles as h over 2 tends to 0. Because as h over 2 tends to 0, notice all these areas are going to shrink, aren't they? Right? So let's see. At the moment, I've got the area of the triangle, this first triangle here, right? That's half AB, so that's r times r squared, sine h over 2, isn't it? Because half AB sine C. This must be less than, from what I can see, the area of this sector. What's the area of a sector? Half r squared theta, and theta is h over 2, remember? Which must be less than the area of this big triangle. But what's the area of this big triangle? Well, I need to do half times base times height. I know the base is r, so half base, and now I need to work out this height here, which is a right angle triangle, so I can use SOHCAHTOA. So this is what I'm looking for. I've got the opposite, well, I'm looking for the opposite, I've got the adjacent. So you can see that tan h over 2 is the same as opposite over adjacent. So the opposite must be r tan h over 2. So here, r squared tan h over 2. Can you see? Now, remember tan h over 2 is the same as sine h over 2 over cos h over 2. Right, that's useful. So here we go. What can we get rid of then? So before we take any limits, you can see that the halves cancel. I can see that the r squareds cancel. All right? So at the moment I've got sine h over 2, I've got h over 2, and I've got sine h over 2 over cos h over 2. Right. Now, I'm just going to do a bit of trickery here because we're not taking any limits yet and sine h over 2 isn't actually 0. I'm going to divide everything by sine h over 2 first. So can you see if I divide this by sine h over 2, I get 1. If I divide this by sine h over 2, I get h over 2 over sine h over 2. Notice that's exactly what we wanted here, but just the reciprocal of it. Perfect. And here, if I divide by sine then that's going to disappear. So that's 1 over cos h over 2. Now I'm just going to flip the inequalities over. So 1 over 1. So this still holds because I haven't divided by any negatives at this stage. Okay. Now we're in the perfect position. The perfect position because I have this sine h over h over 2. Notice it's exactly the same in here. And this is the bit up for debate. So just like before, if I take the limit as h over 2 tends to 0 on the left, then I need to do it everywhere else. H over 2 tends to 0, sine h over 2, h over 2, and limit as h over 2 tends to 0 of cos h over 2. Okay? So can you see on the left hand side, if we simultaneously take these limits, limit of 1 as h over 2 tends to 0, there is no h in 1. So it's just literally 1. It's unaffected by it. Okay? Still got this thing in the middle. So limit h over 2, whoops, tends to 0, sim h over 2, h over 2. And then I've got this side. So as h over 2 tends to 0, cos of 0 is 1, isn't it? Right? 1. So can you see, by the squeeze theorem, we're saying 1 is less than this thing, which is less than 1. So actually, it's impossible for the inside to be anything other than 1. Effectively, we're saying 1 is less than or equal to this thing, which is less than or equal to 1. Can you see it's squeezed between 1 and 1? So for this inequality to hold, which it clearly does, the inside must equal 1. So we've just proven by the squeeze theorem that this whole section, when you take the limit, is 1. And when I take the limit here, as h tends to 0, cos of x plus 0 over 2 is just cos x. And on the left-hand side, on the right-hand side, I'm just timesing it by 1. So we're left with cos x as required. Lovely jubbly. And that's the proof of why sin x goes to cos x when you differentiate it.